So thank you to the organizers for the opportunity to give this talk. For those of you who don't know me, I'm Katherine Fraser. I am a PhD student in theoretical high energy physics at Harvard. And the title of my talk is Challenges for Unsupervised Anomaly Detection in Particle Physics. It's based primarily on work put out last year with several of my collaborators at Harvard. But I'm also briefly going to discuss some ongoing work with one of those collaborators who is a postdoc, Rashmi Mishra. So before I get into details, I want to start with a brief outline of what I'm going to talk about. So I'm going to give an introduction to anomaly detection. I know we've heard several talks about anomaly detection already, but there is a distinction I would like to make that hasn't really been discussed yet. So I'm still going to go over that. Then I'm going to go into two methods for a particular type of anomaly detection called outlier detection. First, I'm going to talk about variational autoencoders, which we heard about yesterday. And then I'm going to go into Wazerstein distances, which we haven't really talked about much this week. Wazerstein distances are a type of optimal transport distance. Optimal transport basically measures the amount of effort it takes to turn one distribution into another. And then finally, I'm going to go to talk about latent spaces, both specifically in the context of the relationship between variational autoencoder latent spaces and Wazerstein distances, but also more generally, why are latent spaces interesting, and what can we ask about them for the purposes of anomaly detection. So first, an introduction to anomaly detection. So kind of as we've already discussed, there's two reasons in high energy physics that anomaly detection is so useful. One is we have such a large quantity of data and our trigger could be missing things, as we heard in the first talk. And the second is we could potentially be looking at the wrong model. Even if we're saving all of the right data, there are an infinite number of models to possibly look for, and it just takes so much time and effort for experimentalists to look for any given model. We can't independently look for all of them. And so the goal of unsupervised anomaly detection, as we've been talking about, is really to avoid this model dependence. And I really want to emphasize that these methods need to be completely dependent only on background. So there's a lot of attempts at unsupervised anomaly detection that train on background data, but then optimize things like hyperparameters based on the signal. That is not completely unsupervised. So if you want a completely unsupervised method, you really need things that are totally signal independent. And there have been many previous attempts to do this through community challenges like the LHC Olympics and dark machines. And these anomaly detection algorithms can really be divided into two categories, finding overdensities and outlier detection. So finding overdensities is what we're more used to in particle physics. This is what you see in your traditional bump hunt, where you're trying to model a background distribution extremely well, and you're trying to find some signal distribution on top of that background distribution. In contrast, what you usually hear about when you're talking about anomaly detection outside of particle physics is outlier detection. So in computer science, for example, if you have a sample of dogs and you're looking for a cat image among that sample, you'd be looking for something that doesn't belong in that distribution. So here, the orange dots for finding overdensities are on top of this blue distribution, but for outlier detection, they are far away. And so both of these are obviously useful. Finding overdensities is particularly useful for answering this model dependence question. Outlier detection can be particularly useful, for example, in the trigger, where we can't necessarily fit the entire distribution of data. So they're both useful in different instances. I'm going to focus on outlier detection because the techniques that we're interested in asking about have been previously applied in that context, but there's no reason that these aren't both interesting questions. And I should also point out that these references here are just a subset of things that I know, so I apologize if I forgot your paper or your favorite paper on this subject. I'm happy to hear about all of them after the talk, but this is just a subset of all the work on finding overdensities and outlier detection. And then one final comment before I move on to variational autoencoders is that we work in the case of a simplified problem. So a lot of anomaly detection tries to work with full events. So you work with events where you have multiple jets and multiple leptons, which is more realistic. But because we really want to understand some of these techniques, we work in the case of just trying to detect anomalous jets. So we take QCD background jets and try to detect top and W jets as your outliers or signal samples. And we use jet images. There are, of course, a lot of other data representations you could use, things like graphs, or energy flow polynomials, or 4 vectors, which are all valid, but images are nice because it's easier to optimize the network sometimes. And we also do some pre-processing, like rotating and flipping those images, discretizing them in order to include the necessary symmetries. And then one comment I also want to make is that we do something that's a little bit unusual, which is normalizing by the total PT. And the reason we do that is that one of the loss functions we use requires that the initial and final PT is the same. Okay, so variational autoencoders. So again, we've heard a little bit about autoencoders. I'm going to go into discuss a few of the basics because I want to both make one discuss some of the notation and also make a distinction that hasn't really been made before. So in the case of an ordinary autoencoder, as we all know, we're compressing info into a latent space and then bringing it back out to the original data, trying to minimize some reconstruction loss. So the notation is that I'm going to call that reconstruction loss in a lot of cases the mean power error, or MPE, which is just a pixel by pixel loss. You're summing up the differences of all the pixels and then raising them to some power, and you can vary that power. And the way the standard story about how this works for anomaly detection is that, the reconstruction fidelity gives an anomaly score. In the case of variational autoencoders, we are again adding to the latent space these distributions that we sample from, which in our case are Gaussians. And then we add a KL divergence to the loss to regularize the training. And the ratio of this KL divergence to the reconstruction loss is determined by this parameter beta, which will be important later. So I want to emphasize the parameter beta. And this loss allows the VAE to be used for variational inference. But the point I really want to make about the distinction between variational autoencoders and ordinary autoencoders is it's this stochasticity that gives distances and latent space meaning. So the fact that you can take a single event and put it at multiple points tells you that those points must be near each other. In an ordinary autoencoder, there's no notion of things being near each other. In a variational autoencoder, there is. And you can see on this on the bottom here, on the left, I have a ordinary autoencoder latent space. On the right, there's a VAE latent space. And this is just the different colors correspond to the different MNIST digits. And you can see there's a lot of clustering on the right and not on the left. And so it's this variational structure that gives these distances in latent space, and we'll be very interested in these distances later on. So our architecture is a pretty standard one. We take a convolutional variational autoencoder that's shown on the left here. We have an encoder with downsampling blocks. Each has convolutional layers, ALU activations, and a pooling layer, and also dense layers that get you to the latent space, and then a decoder that mirrors the encoder to go back up to the original space. But of course, there's been lots of work on variational autoencoders. So why did we write another paper about it? And that's because we wanted to answer a few particular questions. So in this part of the talk, the question we're really interested in answering is how robust is this variational autoencoder? So we want to answer things like, do our results depend upon the type of signal we're working with? So for example, top versus W jets, because if they do, then it's not really truly unsupervised. We'd also like to know if our results depend on the reconstruction loss. So we can use the MAE, which is this mean power error that I defined before with power 1, MSE, the standard, with power 2. And then we can also think about other types of distances for the reconstruction loss, like Wazerstein distances, these optimal transport distances I talked about. And then also, do our results depend on hyperparameters like beta or the number of downsampling blocks? No, of course, any network, your results are going to depend on hyperparameters. But the question that's interesting is, can you optimize them in a way that's signal independent? And that actually turns out to be very, very challenging. And then finally, the other question we're interested in, which I'm going to get to in part 3 of my talk, is can we understand what the VAE is learning in latent space? But first, how robust is the VAE? And to do that, we have to look at some results. So I know this is quite a few numbers, but I want to point out a few things on this plot. So these, in order to characterize how well we're doing an anomaly detection, we're comparing QCD jets versus top or W jets. So that's what these numbers are. We look at both the AUC as well as the signal efficiency at a particular background efficiency. This first column is just for comparison. This is a standard supervised classifier. So that's these brown results. And you can see for both top and W jets, this does quite well. And then these lower rows are for all different training metrics, as well as other hyperparameters. You can see the various different unsupervised results, the blue being the best result for each sample. And what you can see here, so first you can see that the VAE performs best with the MSE loss and 2 to 3 downsampling layers. But what I really want to focus on is the answers to those questions we talked about earlier. So first, signal dependence. What you can see from this is that the supervised classifier does quite well in both cases. You can train a supervised classifier to do either task. But the unsupervised method works much better for top jets than W jets. So it's not truly signal independent. The second thing is this question of what loss metric we're using for the reconstruction loss. And you can see that this reconstruction loss with the Wazerstein distances does worse than the MSE. And maybe that seems surprising because the Wazerstein distances can be presented as more physical, but it's actually okay. And the reason for that is that the variational inference interpretation of the autoencoder relies on this loss being a chi-squared. And so it's okay that we have like a theoretical reason why we should prefer this type of metric. Now we can also ask about other hyperparameter dependence. And it doesn't look like there's too much hyperparameter dependence. These numbers kind of all look similar, so do these. But if you consider another set of hyperparameters, in particular beta, you can see there's actually quite a bit of hyperparameter dependence. So in this plot on the left here, so all these plots are functions of beta. On the left here, I'm plotting the QCD validation loss, and so we want that to be low. In the middle and on the right, we're plotting the AUC of top jets and W jets, so we want those both to be large. The different colors correspond to the different number of downsamplings, 1, 2, or 3, so they're independent curves. And how we optimize our network is by minimizing this validation loss. So we have a totally independent method for optimizing the network that doesn't depend on the signal. And what you can see is these points that optimize the network are plotted on all of these. This point that optimizes the network for QCD does pretty well for tops, but it doesn't do well for Ws. And so what that brings us to is the fact that the choices that best represent the background are not best for signal dependence. And in particular, beta with the lowest loss and validation samples is not best for QCD or W classification. And this is a particular fact about outlier detection. And yes. So the scaling here has to do with the total normalization of the KL divergence versus the number of pixels. So basically, the optimal beta ends up being around where the two contributions are the same order of magnitude. So it's all just a fact about the overall magnitude of beta just has to do with the normalization and the fact that the number we normalize the images to the same total PT, but that's larger than the scale of the KL divergence, basically. Yeah, so, but what this all brings us to is that there is no signal independent way of choosing these hyperparameters, which is kind of a problem with outlier detection and makes training a lot of these networks extremely challenging. Okay, so next I want to talk about Wazerstein distances. So this is another anomaly detection method, but they're also, Wazerstein distances are more general than anomaly detection. So what are they? Wazerstein distances are a type of optimal transport distance. So optimal transport is the minimum effort required to transform one event into another. And optimal transport can be divided into two categories, either balanced, which means that the two images have the same number of pixels or same amount of energy, the input and output image, or unbalanced, where we can create and destroy energy to make for two images that have unequal energy. And so we normalize our image and restrict to balanced optimal transport for some technical reasons. But in principle, you can think about optimal transport in both cases. So more specifically, optimal transport is defined by this minimization of some Fij times Cij. So Fij is a transport plan. It describes where and how to transport intensity. So in this image here, you can see one image is these blue dots. One image consists of all these red dots, and these lines show the transport plan of how to move intensity or energy between them. And then Cij is the cost function, which is how much work it takes to transport one unit of energy, say a Euclidean distance. And so this minimization is over these transport plans. You're trying to find the most efficient way to move the energy. And there have been plenty of examples of optimal transport metrics in high energy physics, including the energy movers distance by folks at MIT, and also more general Wazerstein distances, which is a specialization of this type of distance, where we take Cij to be the Euclidean distance raised to some power p, and then take the whole this whole thing to the 1 over p power. And what this p does is it basically determines what scales are relevant in your problem. So this determines how much you care about differences that are small versus differences that are big. But of course, optimal transport is only the distance between two events. So how do we apply this to anomaly detection? We need to get a distance to a distribution rather than a distance to an individual event. And so to do that, we decide to pick reference samples from our distributions and use optimal transport distances to the references that is an anomaly score. So what do we use for our reference samples? Well, we want to be doing unsupervised anomaly detection. So we choose our reference samples to be QCD images because we want them to be our background. And how do we choose QCD images? There are multiple different things we can try. We can try to take the average QCD image. The other thing we tried is to take K medoids. So medoids are basically, for any sample, you pick some K images, and for every image in that sample, you compute the distance to the closest medoid, and then you keep changing your medoids until you've minimized that. And so basically, you're picking kind of almost centroids images within your samples to try to find ones that are kind of closest to the typical event. And so we find that medoids end up performing better. And the reason for that, as you can see from this, is that QCD images are very sparse. On the left, you can see that. whereas the average image is not, and so it kind of just distorts things. And I should also comment that reference samples have previously been used for other applications, other types of reference samples. So for example, speeding up optimal transport, or comparing to a uniform distribution. But this is the first case of really using this for anomaly detection. And so what do we find here? Well, we like to answer the same type of questions that we answered in the VAE case. So here we have a similar plot. Again, we've got the supervised numbers. Here I'm showing only AUC just to keep this table a little bit smaller, but we have the signal efficiencies in the table in our paper. And we have a similar set of distances. These are the Wazerstein distances and the value of P, the number of medoids, and what you can, and the blue has the same interpretation as before. And so what we end up finding is that the best results use the one Wazerstein metric and slightly exceed the VAE performance, but we find similar trends to before. We see that this unsupervised method performs better on top jets than on W jets, and we also find that we get some dependence on hyperparameters. So you can see that there's quite a difference in results depending on which, for example, which P you choose for your Wazerstein distance, and there's not really a good signal independent way to optimize them. And the reason we find this is that we get worse performance in larger P because small pixel differences become comparatively less important. And this is kind of the same story that you see in the autoencoder case that others have looked at. For example, when you try to train an autoencoder on tops, the reason it doesn't work well is because it's not paying attention to the right scale differences in pixels. This P is the same thing that allows you to control for that. One thing that is a little bit different here is the Wazerstein distances work better than the mean absolute error or mean squared error. And the reason for that is when you're just looking at images, they are more physical. If you're comparing the mean absolute error between images or mean squared error between images, if two pixels are neighboring, they look like completely different. The metric has no way to know whether the pixels are neighboring. But for Wazerstein distances, it can tell that you have this notion. One other thing that we explored in the case of optimal transport was top reference samples. So there have been autoencoders attempted to train on top, but as we all know, that's a very challenging thing to do. In the case of these reference samples, it's actually pretty simple to apply this to a new reference sample. And so basically, we just take the same architecture and apply it to a new reference sample and try to solve the same problem, either QCD versus top or QCD versus W jets, using kind of a semi-supervised approach that assumes W events are kind of more top-like than QCD events. And we basically kind of find similar assumptions. One thing I want to point out that's a little bit different is that which metric works better is different. So here, the higher P metric works better. And again, that's because the scale of differences that you're interested in is different for the top events because they're more stochastic. So you have to pay attention to larger differences only as opposed to the smaller ones. Okay, so finally, understanding the latent space. So what is this autoencoder actually learning? It's kind of one thing that we're always interested in when we're talking about machine learning. It's a black box. And the thing that we found is that the distances between events in the VAE latent space are correlated with Wazerstein optimal transport distances between the same pairs of events. So what I mean by that is you train your autoencoder fully, and then you input all your events, and you get a latent representation of all of them. You take a pair of events, and you compare the Euclidean distances between these latent representations to the EMD distance in the original space. And so that's what this plot on the right is showing. Here's the Euclidean latent space distance, and here's the EMD between the two images. And you can see there's a pretty high correlation here. Now, I should point out that this correlation is not just something that obviously exists. On the left here, we have the EMD of the original images versus the mean squared error of the original images, and you can see the correlation is much lower. So it really is something about the autoencoder and the latent space that you're getting this correlation from. And so this is exciting because it tells us the VAE is learning something physical, and it's telling us something about the type of information that is kind of naturally being learned by this autoencoder. And one other thing to point out here is that it's the downsampling that helps generate these correlations, basically because it helps us associate different scales to each other. I don't have the plot in this slide right here, but basically the way you can see this is looking at the Euclidean distance after different number of downsamplings, and what you find is that you get a dramatic increase in correlation after downsampling once, and also an increase after downsampling twice. So you continue to increase, not every single downsampling because it depends on your scale, but that really is what's correlating these scales and giving you this information. And so finally, very briefly, I'm going to talk about the ongoing things that I'm thinking about which is more generally, I'm interested in asking how latent spaces can help us define the notion of complexity underlying anomalies. It's a very hard question to answer, what is an anomaly? How do we determine if an event is anomalous? And so I'm really interested in developing techniques and ways to visualize and understand latent spaces. So some things I'm currently thinking about are questions like, do these patterns where there's this correlation with the EMD hold for other types of autoencoders or other types of events? Is this specific to jets or not? Can we get additional information by constructing explicit latent spaces? So for example, this paper by Phil Harris and collaborators at MIT compares a semi-supervised approach where you develop a latent space that depends both on a signal and a background, and you're trying to compare both of them. So maybe we can learn more information about latent spaces by doing something semi-supervised, or requiring latent spaces that have specific properties. So this other paper by Phil Harris and collaborators, which was based on ours, basically tries to embed EMD explicitly. So can you get additional information by trying to embed assumptions in your latent space, or should we kind of just naturally let the latent space do what it wants to? And then finally, what are the right tools to study high dimensional latent spaces? What are the right ways to visualize them? So these are all questions that I'm very interested in thinking about. If you're also interested in thinking about these questions, I'd be very happy to chat about them for the next couple of weeks of the workshop. So in conclusion, there's three main points I want you to take away from this talk. First, it's that both VAEs and optimal transport with reference samples, the choices that best represent the background are often not best for signal detection when you're doing outlier detection. And this presents a challenge for unsupervised anomaly detection. Second is that our best results using the event to ensemble distance slightly exceed the performance of the VAE, which is important because you skip this training step. So it can take a long time depending on your autoencoder to train it, depending on what your data is. It's much faster to test this on different things, and you don't have to do the same amount of hyperparameter tuning. There still is some, but it's not nearly as time consuming. So this could be a useful thing to deploy. And finally, Wazerstein optimal transport distances and the VAE latent space distances are correlated. This is actually what motivated us to think about these reference samples in the first place, this very high correlation. But it's also interesting more generally as a potential hint for understanding latent representations. And there's certainly more to exploit here and explore here. And I'm interested in chatting with all of you who are thinking about that. Thank you.
Thank you for the very nice talk and for being really on time. So we have time for questions.
Thank you. Thank you for the talk. I have a technical question, but maybe it's so when you say that like you have better performances for the top end of the W, right, in terms of classification of separation. To what extent this is not expected? That is to say, shouldn't you also quantify in some way how much the top is different from the QCD jet and how much the W is different from the QCD jet, such that maybe one is just more different, right?
So to some extent, it is true that top samples look more, look less QCD-like than W jets. But the thing that's interesting here is this comparison to the supervised result. So in the supervised case, we can get very good tagging for both of them. And the unsupervised result is missing some of that. So, you might still expect this to do a little bit better, but for W, you might still expect your unsupervised algorithm to do a little bit better on top jets, but it's not doing good enough on W jets. I mean, if you look down at the signal efficiency here, it's getting like 0.15, whereas this is 0.91.
Okay, this answers my question. I had missed that line. Thanks. And another thing that you mentioned at some point, I would like you to explain a little bit better. In what sense the latent space of the variational autoencoder, the distance in that space, to what extent is more natural or physical than the distance in the? So can you repeat that maybe? Because somehow so you're sampling, of course, you're giving a distance because you're sampling with the Gaussian with a certain
Yes, sure. So the point that I was trying to make here is that when you have the same event that you can put it in multiple places, because it's the same event, you expect those to be nearby each other in some sense, because you're sampling from this Gaussian. And so you kind of get this spread in your final output space that corresponds to the fact that your latent space has this variability. In an ordinary autoencoder, because every event just gets mapped to a point, you have no guarantee in your output space that, one thing should be mapped to something that's nearby in any sense. There's no way to quantify what's considered nearby because in the variational case, you want to map the same event you want to map one event back to the same thing. And so all these points that are nearby in latent space that are being mapped to this final point, you want them to map to the same thing. And there's no sense of mapping to the same thing in the ordinary autoencoder case.
Since you map one event to one distribution in the latent space,
Yeah.
and then if they overlap for how much, so then you have an error.
Yes.
That's what you mean more.
Yes.
Okay, I think
Questions? Okay.
I have more of a kind of quick comment on the first thing that Andrea was mentioning, which is if you look at your examples for what you get for the supervised
Mhm.
performance, I mean, that is very much the inversion of what the state of the art on supervised top and W10 is. The tops, you do get much better discrimination from the state of the art. Just as you would expect.
Yeah.
They're more complicated. So I'm not.
Yeah, so I guess what I should say here is this is very much not an optimized classifier. The point of having these both here is just to say that you can do very well for both of them. So both of them you're getting, above 90% signal efficiency in AUC. And in the case of unsupervised, you're just not doing very well on the W jets.
But you did mention this as a way to motivate why I should be trying to get comparable performance with an unsupervised method on W tops. And if I compare it to state of the art supervised methods, I don't think that's.
I guess what I mean for comparable performance is that you should do quite well on both of them. Maybe it's not exactly the same, but you should be doing well on both samples. And here you're not. But that is a good
Yes,
clarification. Thank you.
you cannot be doing as well as. And it's like, yeah, for example, in what we are doing, we have always this metric of comparison with how much there is to see in terms of this ideal significance that maybe emerged in some of these talks. And so given that you have a significant performance reduction, you do expect to have it if you are really model independent with respect to if you are model dependent and specific, then maybe trying to get the best supervised top and the best supervised W and trying to go more, because maybe the difference is that one will be 91, the other will be 95, that like on the other side will instead result in the fact that one is seen at 80% and the other at 15.
Mm-hmm.
So maybe you should, so because it's an important point. So if you to try to explore more extensively correlation between how much different the two things are and actually in reality, which means with the optimal classifier,
Yes.
and how much difference you see them, may be more subtle than this table.
Oh yeah, absolutely. I mean, the question of exactly how different the samples are is kind of a separate question from can you do some unsupervised method that's going to at least pick out some fraction of those samples, but that's certainly also an interesting question to explore, definitely.
Okay, I don't see additional questions or okay, there is one there.
Yeah, I just wanted to, you pointed out that MNCs perform better than the Wazerstein loss here because like the reconstruction loss is a chi-squared. I didn't quite follow the connection there.
Yeah, so this is a little bit complicated. So basically, you can basically what you're doing with a VAE is variational inference. And I don't want to get into all of the details of this, but basically you're trying to predict, this probability distribution of your data. And if you do some mathematical manipulation, what you find is that your probability distribution of your data is exactly what you expect from the autoencoder, which is this difference of this probability given your priors minus, this KL divergence term here. And so because you're just looking at this expectation value, it kind of has a natural interpretation when you're comparing this expectation value to use a chi-squared there, as opposed to kind of trying to take some energy movers distance between those two things. Because we're just looking at, we're looking at trying to find, doing something very standard here. And so there's not really a natural sense in where you expect that you need the optimal transport distance in order to model that. It's also much more difficult to implement computationally. And so that also adds to the challenge that, it takes much longer to train. It has much more difficulty finding the minimum as well.
I'm not sure I see how the first term